Huffman codes are optimal for a given source model. So, if the source model changes, then we have to recompute the Huffman code. Therefore, in those situations where the source model is not available or the source model changes, then we have to go for adaptive Huffman code. In today's class, we will have a look at the procedure for construction of adaptive Huffman code. Adaptive Huffman code is constructed on the statistics of the signals already encountered. Theoretically, if we have to encode the k+1 symbol using the statistics of the k previous symbols, then we can recompute the code using the Huffman coding procedure each time a symbol is transmitted. However, this would be a very impractical approach due to a large amount of computation involved. Therefore, it is necessary that we develop a single pass adaptive Huffman coding procedure. Adaptive Huffman code works on the principle that the Huffman code can be represented by a binary tree. So, let us revisit the example which we had studied earlier and where we had shown how to develop the Huffman code for it. So, here is the example. I have a source consisting of 5 symbols and the probability of the symbols or the source model is indicated here. For this source model, we can design the Huffman code which we have done earlier, and the code is indicated out here. Now, from this code we can construct the binary tree representing this code, and that will be as shown here. So, this is a binary tree representing this code. We have external nodes or leaves for the symbols S1, S2, S3, S4, S5. These are the internal nodes and this is the root node. Now, if the alphabet size is m, then there will be 2m minus 1 nodes including internal and external nodes. Now, in this case m is equal to 5, so 2m minus 1 comes out to be 9. So, there are 9 nodes. Now, in order to understand the working of adaptive Huffman code, we add 2 parameters to the binary tree. These parameters are weight of a node and the node number. In order to appreciate the significance of these parameters in the context of adaptive Huffman code, let us first examine these parameters in the context of the binary tree for a non-adaptive Huffman code. So, for the binary tree under discussion, we can associate 2 parameters, weight and the node numbers. So, weight is indicated by Wi and the node number is indicated as Ni. Now, the weights for the external nodes or the leaves corresponding to the symbol is the probability of occurrence of that symbol. So, the weight of S2 would be 0.4 and the weight of S3 would be 0.2. Similarly, the weights of the internal node is given by the sum of the weights of the offspring. So, the weight of the internal node, for example this node, will be given by the sum of the weights of S4 and S5, that will be 0.1 plus 0.1 is 0.2. Now, we will see that in the adaptive Huffman code, the numbering is done in a particular fashion in order to preserve the fixed order of the node. The numbering that is adopted for the adaptive Huffman code is as follows. If I have the numbers given to the node as n1, n2 up to n to m minus 1, then I number the nodes in this fashion in such a way that the requirements on the weight of the nodes satisfy this relationship. W1 is less than equal to W2 is less than equal to W to m minus 1. And in the adaptive Huffman code, this numbering is done from left to right and bottom to top. Now, if we adopt the same procedure for the binary tree under discussion, then we get the following tree out here. I have numbered these nodes from left to right and bottom to top 1, 2, 3, 4, 5, 6, 7, 8, 9, and in each of this node I have indicated the weights. The shaded ones correspond to the external node or the leaves corresponding to the symbol. Now, if you look at this tree and look at the numbering which we have done, then it is very obvious from here that this numbering does not satisfy this requirement where I want W1 to be less than equal to W2 less than equal to Wn, because if I go like this in this manner, I find that W5 is not less than W6 and W7 is not less than W8. So, if we want to number in the same fashion from left to right, bottom to top and still satisfy this requirement, then what I can do is swap some of these nodes to meet this requirement. For example, I can swap the node 5 and 6 and I can swap the node 7 and 8. If I swap the nodes and then reconstruct my tree, what I will get is as shown here. I get a new tree after swapping the nodes. Obviously, the code words for the symbols now change. To obtain the code word for a particular symbol, we have to traverse from the root node to the external node or leaf corresponding to the symbol. For example, if I want to get the code word for S3, then I traverse this way. So, I keep on adding 1 whenever I am the right path and 0 on the left path. So, I get 1, 1 and 0. So, 1, 1 and 0. Now, if you look at this tree, two characteristics can be observed. One is that the node number n 2i minus 1 and n 2i are offsprings of the same parent node or siblings for I greater than equal to 1 less than equal to m. In our case, m is equal to 5. So, for I lying between the range 1 and 5, this property is satisfied. Another property which is worth noting is that node for the parent node is always greater than the nodes for the offsprings, that is n to I minus 1 and n to I. Another interesting property of this tree is that the nodes with higher weights have higher node number and they are closer to the root node. Now, exactly this similar concepts which we have discussed for the non-adaptive binary Huffman code is extended to the construction of adaptive Huffman code. The only difference is that the binary tree corresponding to adaptive Huffman code is dynamic in the sense that both the weights and the node numbers keep on changing. The weights as defined in the context of adaptive Huffman code has to be modified now. So, the weight of the external node is simply the number of times the symbol corresponding to that external node or the leaf has been encountered, and the weight of each internal node will be again the sum of the weights of its offspring. Node numbering is done from left to right, bottom to top. The root node gets the maximum node number, that is 2m minus 1, and it also satisfies the requirement on the weight of the form W1 less than equal to W2 less than equal to W3 less than equal to W 2m minus 1. This property, these two characteristics which we saw for the binary tree corresponding to a non-adaptive Huffman code, these are known as sibling property of Huffman tree or the tree corresponding to the Huffman code. So, similarly in the case of the binary tree corresponding to the adaptive Huffman code, this sibling property also holds good. So, in the adaptive Huffman coding procedure, neither the transmitter nor the receiver knows anything about the statistics of the source sequence at the start of transmission. The tree at both the transmitter and receiver consists of a single node, and that node corresponds to all symbols not yet transmitted. So, what we do is, to start with, both at the transmitter and receiver we have a single node, and that node is called as NYT, which means not yet transmitted and the weight of this node is 0. As transmission progresses, nodes corresponding to symbols transmitted will be added to the tree, and the tree is reconfigured using an update procedure which we will study very shortly. This update procedure is common to both the encoding and the decoding process. Before the beginning of transmission, a fixed code for each symbol is agreed upon between the transmitter and the receiver. A simple short code is as follows. If I have a source alphabet consisting of m letters, m is the size, then pick the values E and R such that m is equal to 2 raised to E plus R, and R is greater than equal to 0 less than 2 raised to E. Now, the letter Sk is encoded as the E plus 1 bit binary representation of k minus 1 if k lies between 1 and 2R, else Sk is encoded as the E bit binary representation of k minus R minus 1. So, if we have, for example, m is equal to 26, then for this the values of E and R can be calculated as E is equal to 4 and R is equal to 10. Now, so if I were to encode the symbol or the letter S1, then since this is the first letter in the alphabet, k is equal to 1, and since R is equal to 10, 1 is less than 20, therefore 1 is encoded as 1 minus 1, that is 0, and 5-digit representation of 0 would be as follows. So, similarly, if I have to encode S20, which is again less than or equal to 20, I have to make 5-bit representation of 20 minus 1, that is 19. So, that will be 1 1. If I were to encode S21, since 21 is not less than equal to 20, then 21 is encoded as 4-bit representation of 21 minus 10 minus 1, that is 10, and that is equal to 1010. Similarly, S26 would be encoded as 4-bit binary representation of 15. Now, if we look at all the code words for this example from S1 to S26, it would be given as shown here. One interesting property of this code is that the value of the first 4 significant bits corresponding to the code word from S1 to S20, these are the 4 most significant bits. The value of this from S1 to S20 will be less than 10. The code word from S21 to 26 will run from, the value of that will run from 10 to 15. Now, this property is utilized for the decoding procedure in the adaptive Huffman code. Another way of coding these letters of this source would have been to use upper flow of log 2 m. In this case, it would have been 5. So, we would have allotted 5 uniform bits to all the code words from S1 to S26. But by adopting the strategy which we have discussed, we find that the code words for S21, S26 utilize only 4 bits. So, we get a simple short code in the process. Initially, all the letters of the source alphabet are placed in the list, and that list is called as not yet transmitted list. That list consists of the letters with the predefined code words for those letters. When a symbol is encountered for the first time, the code for the NYT node is transmitted, followed by the fixed code for that symbol from the NYT list. A node for the symbol is then created, and then that symbol is taken out of the NYT list. Both the transmitter and the receiver start with the same tree structure. The updating procedure used by both transmitter and receiver is identical. Therefore, the encoding and decoding process remain synchronized. Adaptive Huffman code works based on 3 procedures. These 3 procedures are update procedure, encoding procedure, and decoding procedure. So, in order to understand adaptive Huffman code, we have to look into all these 3 procedures. Update procedure is common to both encoding and decoding. So, let us first have a look at the update procedure. the update procedure requires that the node be in a fixed order, and this ordering is preserved by numbering the nodes. The largest number, the largest node number is given to the root of the tree, and the smallest node number is given to the NYT node. The numbers from the NYT node to the root of the tree are assigned in increasing order from left to right and bottom to top. Now, the set of nodes in the tree with the same weight makes up a block. The function of the update procedure is to preserve the sibling property which we discussed earlier, that is the node number n2i minus 1 and n2i are offsprings of the same parent node, and the node number of the parent node is always greater than the node number corresponding to this offsprings. That is the sibling property which is satisfied by the tree corresponding to a Huffman code. So, in order that the update procedure at the transmitter and the receiver both operate with the same information, the tree at the transmitter is updated after each symbol is encoded, and the tree at the receiver is updated after each symbol is decoded. Now, let us look at the pseudo code for the update procedure. So, to start with, we have the first appearance for the symbol. Now, the tree at the beginning consists of a single node, that is NYT, not yet transmitted node. So, first you check whether it is the first appearance of a symbol. If it is the first appearance for the symbol, then NYT node degenerates into new NYT node, an external node corresponding to that symbol. Then you increment the weights of external node and the old NYT node. The next step is to go to the old NYT node and then jump to check whether it is a root node. If the appearance for the symbol is not for the first time, then go to the symbol external node After you reach the external node, check the node number of that external node. If the node number is maximum in the block, then jump to step 4. But if the node number of that external node is not maximum in the block, then switch that node with the highest numbered node in the block, as long as the node with the higher number is not the parent node of the node being switched. After the switching of the node has taken place, if it is permitted, then you increment the node weight. Check whether this node is a root node. If it is a root node, you stop, else go to the parent node of this node whose weight has been updated and repeat the process by going to step 3 to find out if the node number of that parent node is maximum. If again if it is not maximum, then switch if it is permitted, otherwise increase the node weight. You keep on iterating this process unless you reach to the root node, when you stop. Let us look at this update procedure with a help of an example. So, suppose we are encoding the message A, R, D, V, where our alphabet consists of the 26 lowercase letters of the English alphabet. Now, the updating procedure is as follows. We begin with only the NYT node. The total number of nodes in this tree will be 2 into 26 minus 1, that is equal to 51. So, we start numbering backwards from 51 with the number of the root node being 51. The first letter to be transmitted is A. Now, as A does not exist in this tree, so to start with, this node weight is 0 and the number is 51. So, we start with the transmission of the letter A. As A does not exist in the tree, we send a binary code 00000 for A and then add A to this tree. Now, to add the A to this tree, the NYT node to start with gives birth to a new NYT node and a terminal node corresponding to letter A. So, this is my old NYT gives birth to a new NYT and a terminal node, and the weight of the terminal node will be higher than the NYT node. So, we assign the number 49 to the NYT node and 50 to the terminal node corresponding to the letter A. This weight will be 1, this will be 0, and this weight will be sum of the weight of the offsprings, that is 0 plus 1, and the node number here will be 51. Now, the second letter to be transmitted is also A. This time the transmitted code is 1 because A is already existing in this tree. The node corresponding to A has the highest number, that is 50, if we do not consider its parent. So, we do not need to swap this node. So, we just increment the weight of this node, it becomes 2, and we increment the weight of the root node also, that will become 2, and NYT here is 0. 49, 50, 51. So, this is a tree on receipt of A, on transmission or receipt, and this is a tree on the transmission or receipt of A. Now, the next letter to be transmitted is R. This letter does not have a corresponding node on the tree. So, we send the code word for the NYT, which is 0 followed by the index of R. So, if we do that, this will degenerate into a new NYT node and a terminal node for R. This is your R A. Now, so we will transmit 0 and the code word for R, that is code word for R is 1 0 0 0 1. We will look at the encoding procedure little later on. So, I get this new NYT, I renumber this 49. So, this becomes 47, 48. So, the weight is 1, the weight is here 0. I increase the weight of my old NYT, it is 1. Now, this has the highest number in its block. So, I do not have to do anything. I go to the parent node of it. Parent node is this, that has the highest number 51. So, I increment it by 1, come back and check whether it is a root node. It is a root node, so I stop here. So, this is the tree which I will get at the end of transmission R. Now, when I transmit the letter D, again the transmission of D is for the first time. So, we have to send the NYT node. To send NYT node, we have to send the code as 0 0 followed by the code word for D, the code word for D is 00011. So, in the next step, this node 47 will give birth to a new NYT and a terminal node. This terminal node corresponds to D. So, I update the weight of this. This will be 45, this will be 46, then the weight of the old NYT is 1. I look at the parent of this, the parent of this is this. Now, that has the highest number in the block. So, I just increment the weight, that becomes 2. So, this remains as it is. This again has, once it becomes 2, it has the highest number in the block. So, I do not require anything to be done. Now, I go to the root of parent of this node, that is this node. So, 3 it becomes 4, and these numbers are as follows. So, this is a tree which I will get it on the receipt of the symbol D. Now, the next transmission is V. Now, the transmission of V, again V is not existing in this tree. So, what will happen is that we have to send the code word for NYT, which is 000, followed by the code word for V. Now, so this node will give rise to a new NYT plus a terminal node corresponding to V. So, let us do that. So, this node now will give rise to a new NYT and a terminal node for V. So, I will have the numbering as 43, 44, 45. This is my NYT. This node corresponds to V with the weight V 1. This is 0, 1, 1, T, 49, 47, so this gets degenerated, that was the old one, into new NYT and V. I get the weight for this old NYT as 1, move over to its parent. Now, if you look at the parent of this node, it does not have the highest number in the block. The highest number in the block is being possessed by the node number 48. So, I have to swap it and then increment. So, if I do that, what I get is so I have swapped it so I swap this node, and after I have done the swapping I increment the weight of this node. So this becomes, this is R, this is the weight, that is equal to 1, and this becomes 47, this becomes 48, this becomes 2. Now after I have incremented the weight, I look at the parent node of this, the parent node of this is this. Now again this node does not have the highest number in the block. The highest number in the block is possessed by the node number 50. So I have to swap this node with 50 and then increment the weight. So if I swap the thing with 49 with 50, then what I will get is as shown here. I swap the 49 with 50 and then increment the weight of it, so that becomes 3. After I have incremented the weight of this, I go to the parent node of this. So the parent node of that would be the root node. See if it has the highest number. It has the highest number. So I increment the weight of this node, that becomes 5, and then check whether this is a root node. Since this is a root node, I stop. So finally the tree which I get is shown here on the transmission or receipt of the sequence of symbols corresponding to AARDV. Now if the next symbol to be transmitted or to received is A, then we send the code as 1 and then look for this whether it has got the highest number. If it has got the highest number, in our case this will be 49, this has the highest number. So we don't do any swapping, and then we just increment the weight of this. So this would become 3, and then check for the parent node of this node, and that would be the root node. Again this is the highest number, so we just increment that and check if it is a root node. Since it is a root node, it will stop. So in the next alphabet to be transmitted, the next letter which would to be transmitted was A, then that stage the tree would look exactly like this, with the weight of A increased to 3 and this to 6. Now this updating procedure which we have studied with the help of an example is common to both encoding and decoding procedure. Now we will have a look at the encoding process and decoding process, which is a part of the adaptive Huffman code, in the next class.